Bismillahirrahmanirrahim. Assalamu alaikum. Now we will discuss in today's lecture, that is lecture 5. We continue to discuss Aashto method rigid pavement design 1998. Now the next parameter is the subgrade value, and here in rigid pavement we take subgrade value by performing plate load test. Plate load test is a simple test in which the your subgrade is loaded by a rigid plate. This can be a 30-inch plate, 24-inch plate, 18-inch plate, 12-inch plate. Then there is a force, and this force is applied to the subgrade through hydraulic jack. And this pressure is noted. And whatever deformation we have with this pressure, we try to know it, and then we draw a curve and calculate the subgrade value. Again, if you do not have the facility, then you can use the relation as 1500 CBR times CBR over 26, and that is 0.7788. So this subgrade value measures the supporting power of subgrade, subbase, bases, and a complete pavement. It has an advantage, it can be performed as a field test. And these data from the test are applicable for design of both reflexible and rigid pavements. And then we also need some corrections. So what you do, you keep on deforming the pavement through hydraulic check, and we note the stress. Now the K values is calculated when the pressure is 10 psi. So whatever is the pressure at 10 psi, we will like to know the deflection or deformation in inches for this 10 psi. This is a standard pressure needed to calculate meters of subgrade reaction. Or alternatively, if you do not have K value, you cannot have a test real value of K modulus, you can estimate by using this relation. Now once you get the subgrade value, in a rigid pavement, you can modify it for a subbase. So if you have a 4-inch subbase value, if you have a K value of 50, then you can use 65 as an input for subgrade reaction. So actually this 4-inch and 6-inch or 9-inch and 12-inch of base provide improved value in the support to the subgrade. So that's why if it is 100 psi and for 6-inch you can take as 1 form. So on and so forth. So from this you can also say that you can provide a maximum of 12-inch subbase in a rigid pavement. The third characteristic, the third parameter is modulus of rupture, abbreviated as S-C. It is the value of flexural strength of Portland cement, and it is taken as 650 FSI for the practical purposes. Then the modulus of elasticity you can evaluate by performing this test method, but in practice you don't do it. And there are a range of values between 2 to 6 millions, and we take 4 million. This is an average, 2 to 6, the average is 4 million PSI. Now the reliability, what happens is that as we construct the pavement, this reliability curve can be like this or can shift to like this. So that's why this is the factor of safety we use for rigid pavement design. Again, the reliability concepts are the same as for a flexible pavement, as we already have discussed. The design reliability values is also associated with standard normal deviate, likewise in flexible pavement. So if you have 50% reliability, you can take a zero value, and 99%, you can take minus 0.32. See, normally we take between minus 1.282 and minus 1.645. You must be wondering that in the previous example, we don't use this value, likewise here, but this is for your knowledge purpose. At this level, since we will be using nomograph, will not be required the value of standard normal deviate. The drainage coefficient, uh, again, you can take any between value between 0.8 to 1.1, but normally we take 1.0 as a good value of drainage design. Standard deviations, this standard deviation has the same concept, and yet again it is for poor traffic prediction, material variability, and for rigid, this will be taken as 0.35 for a new pavement design. I hope you remember why we take standard deviations, and we have discussed thoroughly in the flexible pavement design. Similarly, the load are characterized in the same manner. The procedure for calculating the ESLs are the same. So that's why I'm not repeating it. This is the same as we already have done previously. Another parameter that is required is a load transfer coefficient. And this load transfer coefficient is a slab ability to share its loading, with neighboring slab. As you can see, what would happen if there is no dowel in between these two slabs. This is a longitudinal sections. So if the vehicle is moving in this direction, this slab will deform and this will remain at space. And once this wheel move to this position, this slab will go down. So in order to have a uniformity in the load transfer, we use this connection. This is a load, also what we call a dowel joint. Can be from aggregated interlock, tight concrete shoulders, and extended limb has the same effect. The load transfer coefficient values can be varied from 2.8 to 3.6, and if you take the average, you can take as 3.2 as then average value. For non-dowel joint, this will be obviously more, 3.6 and 4.2. Normally, you don't take risk in non-dowel joint, but for CRCP payment, just we do have this non-dowel joint. So we say all PCCP having easels greater than 1 million, we require dowels. Most pavement should be doweled. The pavement has shoulder. The shoulder must be Portland cement concrete. On one major advantage of unstained Portland cement shoulder is the reduction of slab stress and increased service life they provide. Now, I have summarized the values for rigid pavement design. So, traffic 18 kilopound, equivalent single axle load of 18 kFs. Now it is calculated from traffic data, as you know. Terminal severity between 2.0 to 3.0. Modulus of rupture, use 650 psi. Then modulus of elasticity, this we use between 3 to 4 million. Just pardon me about this value, I will correct this. Then modulus of subgrade reaction, you will know from your CBR values using this relation. Reliability 80 to 99%, usually we take 90 to 95%. Overall standard deviation 3.35, load transfer coefficient 3.2, drainage coefficient 1.0. If you like to have standard normal deviate ZR, you can consider that table. Loss of support, we are not doing it. So let's don't discuss it because it is sometimes something of advanced level. So just ignore this loss of value support. And initial serviceability PI, as I discussed, is taken as 4.5. Now let's do an example pavement. How to design a rigid pavement. A 4-lane pavement is expected to carry the traffic of 50 million vehicles. It is to consist of PCC with elasticity modulus of 4 million psi. The CBR strength is 15. It is estimated it has average drain condition. It has a reliability of 95% and initial stability 4.5, while PT is 2.5. Use the nomograph to determine the thickness of the surface layer, and you also would like to provide 4-inch subbase. First thing first, solution step 1. Calculate delta PSI, likewise P0 minus PT, and it becomes 4.5 minus 2.5, this becomes 2.0. Reliability, for 95% reliability, and we will be designing for standard deviation 0.5. Estimated cumulative traffic, and this is already given to us, and it is 50 million vehicles. We would like to know the value of K, and since CBR is given, we come up with 200 psi, but since we have a 4-inch subbase, so we'll improve this, and from the table I have shown you in the last lecture, you come up of this value of 224 psi by interpolation. The material property, as we've discussed, KIPS means, KSI means kilopound. So what we do is just divide by 1000 to get this in KIPS. Right? Drainage coefficient 1.0, load transfer coefficient 3.2, and the modulus of rupture 650 psi. Now the nomographs is different from that we have used in Aashto flexible pavement. There are two sets of nomographs. Actually, there are two sides of nomograph. The first page, this is figure 1. We enter with the subgrade direction, go perpendicular, intersect the appropriate elastic modulus, and then we go perpendicular, and that is what we call a tunneling line. At the end of tunneling line, a line is taken to the appropriate load transfer coefficient, and then this line is extended to the next line. Again, we have a tunnel line. We intercept the drainage coefficients and extend to the line to the match line. This is where figure 1 and figure 2 will meet. So we have a match line. So wherever we start from figure 1, wherever we have stopped at figure 1, we'll start the figure 2 with the same line. From the match line, the line is extended to appropriate PSI to the design thickness chart. A horizontal line is then plotted. Enter the nomograph with the reliability value and proceed through the overall deviation and intercept the tunneling line. From the tunneling line, intercept the appropriate 18 capitals and extend the line to the design slab thickness. Extend a vertical line upward, intercept the horizontal line. This deception gives you the design thickness. Don't get confused. We'll be using, and this is very simple. I will show you in the next slide how we actually do it. So this is figure 1. So what we do, we have taken this value of 224 psi. Again, this is 100, this is 200, this is 250, so it's 220. At least 224 but for the sake of simplicity, I have taken this. I've gone perpendicular. I've tested the values of class system modulus, that was 4 million, and then I turned perpendicular. I've stopped here. I know my modulus of rupture 650, so I've connected this point to this point, and I have extended to the transfer line. I will stop here. Now I will join this point with a load transfer coefficient, that is 3.2, and I will extend here. I will stop here. After that, I will again, since I know the value of CD, I will locate 1.0, connect this line, and I'll stop this mesh line. This is around 72. Again, you start with modulus of separate reaction, do 24 psi, draw perpendicular, intersect the curve, and whenever we intersect, we go 90 degrees. So we stop here. We located 650 psi, join these 2 points to get another point. And then from this point, we located 3.2. We extended to transfer line here. Stop. Then from transfer line to drainage coefficient, here 1, connect these two, and you will stop up this value around 72. Now, the next slide, we start where we left off in the first nomograph. So from 72, you go design serviceability, delta PSI, stop here, and then you draw a perpendicular, just in this direction. So once you have done this, now then you start from the bottom. So this is how you read this figure 2. Start with the match line, connect serviceability, extend it to the y-axis of design supply thickness, and draw perpendicular. Then from the bottom, you again you locate your reliability, join to standard deviation, stop here. This, then design, connect this chip value, and you stop here. Remember, in Aashto rigid pavement design, you can go up to 50 million pieces. 50, actually, it's 50 bill. You can say 500 or 500 missile or 1,000 million e-cells, right? So you can say 1 billion e-cells. So this is why that's why we prefer a rigid pavement or flexible pavement, because in flexible pavement you can design up to 50 million e-cells. Anyhow, so what we have done is, once we have stopped it, connect with 50 million, we stop here, and then on this axis we'll draw perpendicular. So what happens is that whenever these two lines intersect, this is the thickness value of our pavement, rigid pavement or a PCC base. So from here you can see it is 13.5. And again remember, you will use this nomograph from both sides, first from the matching line and then from the bottom, connecting step by step and to get this intersect. It's a bullseye. So what next? Again, since we have calculated 13.5 inches, you consider as 14 inch. Again, we will design this pavement section, but this is a rigid pavement section. It will have 2 layers, 14 inch that we have calculated, 4 inch was already known to you, and this is a typical cross section of rigid pavement. So, you know, there is not much difference in the cross section. It is the layers that are different, and obviously the materials are different. So if you know to design the section of flexible pavement, you also know how to design rigid pavement. Just you have to just delete one layer, extra layer from it. So this ends our discussion on pavement design. In this part, we have discussed both flexible and rigid pavement design. Now, our next topic is a very important topic, and it's about highway. Okay, before I move on it, This one more thing I need to discuss, that minimum thickness of concrete pavement is 8 inches, and the less, so 6 inches if you have a driveway sidewalls. So normally, even if you do not get values of 8 inches in rigid pavement, you just provide 8 inches, because the value not of less than 8 is usually not considered in for rigid pavement side. Or we can say if it is less than 8 inches, better we have a flexible pavement, because it becomes too uneconomical and too over designed, too much over designed for any traffic condition. Now, we'll discuss highway drainage. It's a very important part. You know, one of the reasons why our pavement fail is the lack of adequate highway drainage system. What is the need? Highway drainage consists of removing or controlling surface water, the water that's coming on the surface and subsurface, and from the road surface and subgrade supporting it. So there is a surface drainage and there is a subsurface. So what happens is part of the rainwater flows on the ground while other percolates into the ground and reaches the groundwater table. Remember, in flexible pavement, we were considering drainage values. We want water to, to drain out. Remember, this is because whatever you do, how much, no matter how you think your pavement is unpavable, but the actual pavements do let some water to seep in. So that is where we said provide a drainage layer, base course and sub-base course, have a drainage coefficient, and that's why we this water will be taken care from that coefficients, and that extra measure that we'll discuss in this section of our lectures. So whatever happens is whenever the water reaches the ground, it raises its level. Now we have to control this water as well. Now highway drainage redirects water into appropriate design channels, eventually discharges into natural water systems like canal, river, and ultimately to the sea and oceans. Why important? Because it can damage to the highway structure, it can cause loss of capacity, visibility problems, safety problems, reduced friction, and hydroplaning. Hydroplaning means water standing on the road, and people may have a difficulty in driving through this condition. So we'll discuss what are the highway drainage types. In the hydrologic cycle, a part of total precipitation or rainfalls runs on the ground. This portion is called the surface runoff. We get collected in tanks, lakes, reservoirs, and other such bodies. A part of this way runs off from streams and joins running water in the form of rivers, which eventually join the seas and oceans. All these constitute surface water. Similarly, the remaining part percolates into the ground surface, where favorable condition of permeability exists. This water joins the great groundwater table and groundwater reservoirs, raising the groundwater table. In the dry summer season, groundwater level rises due to capillary. However, the exploitation of groundwater by humans depletes the groundwater and lowers the groundwater table. Once again, during this season, it gets recharged by percolation, raising the groundwater table. This groundwater table, on one hand, is detrimental to the pavement, while on the other hand, it is a higher water table means more water resources for the people using it. There are three principal types of highway drainage: surface drainage, subsurface drainage, and the cross drainage ones. We'll discuss in detail one by one during this course of my lectures. So what is the requirement of good drainage system? Reduction of strength, spoiling the pavement by formation of potholes. If you have a good surface water, this will not happen. Tipping of surface through pavement layers, shoulders, and slides into the subgrade. Reduction in the bearing power of the subgrade. Volume changes in the subgrade. Consequent settlement. Soil erosions around the pavement. The embankment are broken, and if once the embankments, the sides are broken, the pavement will lose the support, and naturally it will subside. There will be no pavement. You must have heard the pavement being washed away from the floods. This is why if you don't have a proper highway drainage system, this would happen. Slope failures in the case of cuttings, and capillarity and force. Capillarity is the reverse flow. When you have a subgrade soil like clay, the water comes through it. It's just like water rising in a thin tube from the uh, water tray or water tank. And eventually, this weakens the subgrade, and once it gets to the subgrade, it will reach the pavement from the bottom, and it will destroy the pavement. There will be no loss of support, and that's why we need a very good drainage system. So normally, the design considerations you need is a transfer slope. So remove water from the pavement surface as early as good slope, and this is the cross slope. Must have been discussed on the geometric part of your uh, highways, as been taught by Dr. Misha Bareli. These are cross slopes and then the shoulder slopes. Then there is a longitudinal slopes along the length of the pavement. Even if you have a level section, you provide at least 1% gradient so that the rainwater should flow not only transversely but longitudinally as well. Then there are ditches along sides of the road to collect surface water after runoff. This is what we call a transfer slope, and this is a ditch. You can see just a depression so that water is collected from here to here. Then I said along the length of the road, you provide a cross slope or longitudinal slope around 1% so that the water will flow in this direction. So one of water should also from here, and it will be dischargeable. Sometimes we also provide there is a drainage here. So at some instances, the you just keep on collecting the water from this drainage channel, and then it is again connected to this. There is a longitudinal channel as well here. This channel is connecting. This is what I'm saying. Actually, this arrow should have been here. So this is a longitudinal channel where this water will be collected. And actually, it will be connected to the manholes, and then it will be connected to the other water bodies. Like this. Now we'll discuss surface drainage. It consists of arrangement of made for the quick and effective drain of water that collects the pavement surface, shoulders, slopes, and cuttings and adjoining line up to the right of way. This water is let into the natural or artificial channels sufficiently farther away such that the functioning of highway is not impeded in any manner. The source of waters are normally rain, snow, drizzle, hail, and sleet. Wastewater from irrigation is also a possible source, and in our system, the water flowing out from the manholes, sewage water is also a water that we need to collect. Even though the best solution is to connect those sewerage lines, but again, this is something it's beyond our hand. So, as a highway engineer, taking into consideration the local conditions, we also take care of this this extra source of water. We need to take care of this, otherwise the pavement will get damaged. And then slow falls and melting ice are also common source if you are talking about the road in the mountainous areas. There are three phases. First, to know how much quantity of water will reach your pavement. You have to design the systematic element of this surface drain system, and then you have to compare different materials to serve the purpose. So have to have desire to have steep slopes, provide good hydraulic capacity and lower right of way cost, but reduces safety and increases erosion and maintenance costs. So even though we would want to provide the steep slopes, but sometimes because of this economic, we cannot provide. And also not only the economic, but also the vehicle may slip away in some extra country. So that's we need to take care of. It's a very simple equation. You must know it from hydraulic course. It's we call CIA, where Q is the runoff. We say QSEC, cubic feet per second, or QMAC, cubic meter per second. This is the metric units, and these are English units. So QSEC is this, and QMAC for this value. This is a drainage coefficient, depends upon the area. Usually it can be as low as 0.2 and it can be as high as 0.9, depending upon the, the materials surrounding your pavement. Then there is the intensity of rainfalls, uh, inch per hour or millimeter. It varies from different areas to different areas. And there is a drainage area, the acre or hectares. The water, we will estimate the water is coming from onto the pavement. Uh, a detailed design or example is beyond the scope of this course because you already have courses on hydrology. So I will just keep my discussion to this value in order to know, just to give you the concept how we estimate the water flow on the pavement. Now, transfer slope is a very integral part of the pavement. Uh, so we have for undivided highways, that is having no medians, have a crown in the middle and side slope downward towards both edges. This cross may be plain or rounded or combination of the two. For one-way travelway or divided highways may be crowned separately or may have a unidirectional cross slope. You will see in the figure, and inshallah this will clear your concepts. That is what I mean. This is 2% slope. So what you raise this pavement 2% with respect to this pavement. So whenever the water flow, there is no medians. So the drainage will be on this side as well as on this side, and you allow water from center line to go from here and to here. Then, if you have a one-sided drainage system, or you are talking about the pavement on the curve, you always provide super elevation, and then you raise the outer edge. So this is where actually you direct the water wherever is your drain. Sometimes this is what we call a super elevated section. Now, sometimes, but I've said that you have to make around this rollover so that there is no straight edge connecting these two slopes. If you have two slopes on the other sides, you have to round it like this. Now, if you are divided section, sometimes what you do, you provide median, you have provide a drainage in the median as well. So part of the water, part of the slope from this travel way, part of the roadway will be raised. Part of the water will be collected from this drain and part from the outside drain. So this is normally for the pavement there are more than 4 lanes. It's economical to have this. So you have a slides, you have cross transfer slopes on both the sides. So each pavements have two ways slopes. So we stop here. We'll discuss the drainage channels and side slopes in the next set. Hope you have understood the concept of the rigid pavement and the concept about highway drainage. So I'll stop here. Uh, this was lecture 5, and in lecture 6, inshallah, we'll discuss highway drainage, more topic on highway drainage.